Hi, can you hear me? Okay, we can start. You can hear me, right?
Yes, sir.
Okay.
Yes, sir.
Okay, so as I mentioned on the group a few days ago, I would like to conduct a small test. But sorry, my voice is not in a very good shape, but yeah. I want to conduct a small test on next Sunday. It will be part objective and part subjective. So, right, just a few questions, maybe 5 questions objective. But the main goal of that exam is to test what is your writing skill like. Because in the online format, that is a bit hard to assess. That I can hear what you say when you describe the solution, but being able to actually see what is your working is very important. And so I want that opportunity through the next week's test. Okay, so as far as possible, we'll try to have the exam in person in one of the MPI classrooms. So I'll let you know. And the portion, so to say, will be basically mostly number theory, what we have been doing so far. I might add just a couple of questions of geometry commentaries. Nothing too difficult. I mean, we just to test how good you are at writing those kind of problems. Okay, so that is the focus. Okay, so then coming to. Sorry, you are saying something?
Yes, sir. Is it possible to conduct the test from 9 to 11?
I'm fine with that. Is everybody okay with that?
Sir, it might be difficult for me.
Okay. See, we can do one thing. This is just an internal informal test. There is nothing like everybody has to start at the same time. I'll be there on the classroom from 9 onwards. You can come anytime, start writing your test, and once you are done with 2 hours, you submit your paper. Okay. So whoever wants to start at 9, start at 9. Whenever you reach from that point, you will be writing for 2 hours. Okay. So we'll keep it flexible that way. And in fact, I'll give you the flexibility, like 2 hours is just an arbitrary number. Right now, for me, what's important is that if you are given enough time, can you solve the problem? So somebody wants to take more time also, that is fine. Instead of 2 hours, somebody wants to sit for 3 hours, 9 to 12, that is also fine. Okay, so take all the freedom you want. Yeah, but we'll conduct the exam on next Sunday. So just a minute, I'll send you a link to the, as I said, every year I have these lecture notes in which I keep documenting what are the overall topic or outline of the properties that you have done. So that will be like a good reference for you to know, just generally speaking, that what have you covered so far. But that is not a complete replacement for your own personal notes, because this is just an outline. But and you have to supplement this with lots of practice problems. As I already mentioned that David Burton's book is one very good source for that. And maybe in another 3-4 weeks, when we are done with the basic theory, we'll look at actual RMO and other problems also. Okay, so I just posted a link on the group where you'll find all the notes which I have made. And I keep updating this. So as and how our lectures are proceeding, I may want to rearrange few things or make any additions. So I keep doing that. But at least you can get the updated version. Okay, so then continuing with the discussion that we were having last time about GCD. In particular, there was one property that we were talking about is that if you take the GCD of any two numbers, that number itself is a multiple of any other common divisor, and we were looking at how we can try to prove that. And I think Arnav mentioned that one proof, I mean, standard in most number theory literature will find something called Bezos Theorem, which we are going to do now, which is used to do that proof. But I thought let us try without Bezos Theorem. I honestly didn't remember whether it is possible to do it without Bezos Theorem or not. And I think Raghav submitted one very close attempt, almost complete, but there was just one small issue. But I mean, through similar ideas, it is possible to do it without Bezos Theorem also. So we'll look at that. Okay. So before we go to that, just want to list out what are all the tools that we know so far, because honestly, sometimes in this very early number theory, a lot of things we know intuitively already from like school syllabus, and we may end up making the mistake of using some property which we have not proved so far formally. Okay, so the order of events is very important. I mean, for example, I think last time some people were suggesting using prime factorization to do this GCD and LCM. But I mean, when we do the topic of primes, we may end up using the properties which we are proving right now. So I mean, we don't want to get into that kind of confusion of the order of what we prove first and what we do next. So if I write down what are the things that we already know so far, so tools we already know. So I mean, the very first thing we did was well ordering principle and induction. Then when we started with divisibility, the very basic thing was division algorithm, which is just the existence and uniqueness of a divisor and quotient. Okay, then we came back to divisibility. So things like basic properties like A, if A divides B and C, then A divides any linear combination of B and C. And then we also define what is the GCD. So GCD of two numbers. We just defined that. We did not actually start proving any properties related to that. So this is pretty much all we know at this point. Okay, we don't know anything about prime numbers or anything else. So whatever you want to do, we want to use these things only. Okay, and then the question we were asking last time was that, so if let's say D is the GCD of two numbers A and B, and let some G be another common divisor, of A and B, then our claim is that G has to be a divisor of D also. This is what we're trying to prove. So does anybody have any new ideas how to approve this using just the what I described above, the four properties above? How can you use those things? So why don't we get started with the proof and let's see where we get stuck, and that might give us some idea what to do next. So like we can do this as a proof by contradiction. Okay, so let's say if possible, so if possible, let this not be the case. Let's say D is not a multiple of G. Okay. Now, in general, if you have any two numbers A and B and you take any two common divisors, there is no reason why one has to be the multiple of the other, right? What is the special thing that we know here which have to exploit somehow? What is special about the G and D? In general, any two numbers you take, the list of common divisors will be large, and there is no reason why one has to be a multiple of the other. But what is there in this question that which make these two numbers special? Okay, so what is important is that D is not just a common divisor, it is the greatest common divisor, right? So the fact that the greatest is the important part. If that greatest was not there, then this question doesn't have to be true. So that is what we have to use. And I think Raghav, that is what your proof was trying to do, right? I mean, you
Yes,
want
sir.
to find a common divisor which is even greater than D, and then that is the
Yes, sir.
contradiction, correct?
Yes, sir.
So that is what we want to do here also. And in fact, the divisor which you had suggested was the right one. So I think what we had done was if you take the GCD of G and D, right? So let D1 with the GCD
Yes, sir.
of G and D. And then what was the divisor that you had proposed?
So one second. Then I've said that G over D1 and D over D1 is equal to 1, the GCD.
G
By
over
definition.
D1. Yes, correct. Because when you take away the GCD, the remaining part will be co-prime. Okay, then
So I said let G over D1 be equal to K.
G over D1 equal to K. Okay.
But then I said that K divides G and G does not divide D, so K does not divide D.
Right.
But
And
then
I
I
think
told that that was wrong.
yeah, correct.
So
So,
I
but
was
yeah,
not
I
able
mean,
to.
that part was wrong, but the suggestion was on the right track. So, what is the new divisor we need to look at? So, by the way, yeah, here we find G by D1 equal to K, and then we are talking about KD, right?
Yes, sir.
So, if I just write KD in a different way, if I substitute the value here, it is basically GD upon D1, and D1 is nothing but the GCD of G and D. So, what does this number look like, everybody?
The LCM of
The LCM.
It looks like the LCM, right? So the suggestion here seems to be that what if we consider the LCM of G and D? Okay, so instead of going through this calculation, let me directly say let capital D be the LCM of G and D. So now the only thing is we have not defined LCM formally, but I think everybody knows the definition, right? So I'll just add it to the list. Just the definition. So the LCM of two numbers is the smallest number, which is a multiple of the both numbers. Okay. So I just need a definition of LCM. I don't need anything else. And that is what I am saying as D. And my hope is that suppose we can prove that D is also, this capital D is also common divisor of A and B. Then will that complete our proof?
Yes, sir.
Because what will happen? So I'll erase this middle part. And let's say directly from here I come to, if possible, let this be. And now, of course, I have to prove this, but suppose I prove that D divides A and D divides B. I mean, in other words, D is a common divisor of A and B. Then what will be the next step? Yes, Raghav.
So you know that G is not. So you know that G is not a factor of D. So
Yes.
the LCM has to be greater than D.
Yes, correct. And that is a
It's not
contradiction
possible
because
since D is the GC.
yes, correct. Does everybody follow? See, we are making full use of the GCD part of small d, right? Any number greater than small d cannot be a common divisor. And if this capital D is the LCM of G and D, you all know that when one number is a multiple of the other, then the larger number is the LCM. But if because we are assuming that G is not a factor of D, therefore this LCM has to be greater than D. So that will be the contradiction that we have found number greater than small d, which is also common divisor. Right? So the only missing piece is we have to prove this, right? Once we prove that D divides A and D divides B, we are done. Okay. And A and B are symmetric, right? So we can do only one part. Let's say I want to prove D divides A first. So maybe I'll give you a few minutes to think about this. How can you try to prove D divides A? Okay, Raghav, you already have a solution? Let's give others
Yes,
some time. But everybody follows that this is the only step required to complete this proof. Looks like we have less number of people today. Is there some conflicting exam or class?
Sir, I have an exam, so I have to leave my house at 10.
Okay. Okay, so can we proceed by contradiction here? Let's say we want to prove D divides A. Suppose that is not the case. Okay, so if possible, so this is actually your proof by contradiction within a proof by contradiction, but that's okay. So this is what this is like a lemma, you can see that sub part. So to prove D divides A, if possible, let that not be the case. So then what can I say? I can use division algorithm and find the remainder and quotient. If I divide A by capital D, I'll get some remainder and quotient. And because we are saying that if possible, let this not be a multiple. So what are the restrictions on R?
R is non-zero.
R is non-zero and also
and-
less than capital D, right?
for the
Yes.
Okay. Then, and what do we already know about this small a and d? What can we say? Okay, so now I want to make use of the fact that D is given to be the LCM of G and D. And I have got a number R which is even smaller than D. Can you see that R is also a multiple of G and D? So my claim is that R is also a common multiple of G and D. Do you see why that will happen?
yes,
Because let's take G first. So in this equation, right, A equal to dq plus R. See, G already divides A because G is going to be a common divisor of A and B, and G divides D because D is the LCM of G and D. So G already divides this part and this part. Therefore, G has to divide R. Similarly, capital D, sorry, small. Similarly, small d also divides A, that is given, and small d divides capital D because capital D is the LCM. So therefore, small d divides R also. So what are you saying, that G and small d, they are both dividing R? But is that possible? Because then what does that mean? R is also a common multiple of G and small d, but it is smaller than capital D, right? Which contradicts the definition of LCM. But as D is the LCM, R less than D is a contradiction. Okay. So therefore, what it means, the only choice is that R has to be 0. Or in other words, therefore D has to be a divisor of A. And by similarly, same thing will happen for B also, right? There is no difference. So similarly, D is also divisor of B. So have we completed all the proof now? Because therefore D is divisor of A and B, which means that D is a common divisor. And if D is a common divisor, it has to be less than or equal to the GCD of A and B. So D divides and D divides B. Therefore, D is a common divisor of A and B. Therefore, D has to be smaller than or equal to D, small d. And the only case when the LCM is smaller than or equal to the number is when the number is equal actually. So therefore, the only option is D has to be equal to D, and which implies G divides D as required. So actually, in a way, I initially wrote it's an indirect proof. We can write it without referencing the indirect part also. Okay, I'll give you a few minutes to copy. But I hope the overall logic is clear to everybody. What we are doing first, what we are doing next. But this is a very interesting property, right? That every common divisor of two numbers is also divisor of their greatest common divisor. That's what we are saying. Can you think of something similar that may happen for LCM? If you take the set of all the common multiples of two numbers, yes, Raghav?
So the LCM will divide all the other common multiples.
Yeah, exactly. So if you go to my sheet, you find. So what we proved right now is this with 0.4.3. Every common divisor of two numbers is a divisor of the GCD. In the same way, I am claiming this. Every common multiple of two numbers is a multiple of their LCM. Okay. Maybe actually the proof of that is very similar to what we did just now. So maybe just a couple of minutes, maybe you can try quickly to do this. Okay, so in general, all the 4 points of this point 4, you can see all of them as related to each other. That's why I grouped them together. That there are some properties about GCD, and there's a very corresponding, like one-to-one correspondence with the properties of LCM. So what we just proved right now is actually point 3 and 4. I mean, while we are proving point 3, we actually use point 4. That if there are any two common, point 2, if any two common divisors are there, then their LCM is also a common divisor. By the way, to introduce this notation, I don't know how universal this is, but at least in some literature I've seen this. Round brackets are used for GCD. Okay, so when I say round bracket, this is the GCD of A and B, and square brackets are LCM. Okay, at least in our class we will use this notation. If you are going to use this in exam, just state this at the start of your solution, that this be the symbol for GCD and this for LCM. Just makes things easier to write. Okay. So can you prove this part? Every common multiple is also a multiple of the LCM.
Can you wait for 2 minutes?
You want more time?
Yeah.
Yeah, sure. So our claim is that if let A and B be integers, and let's say capital L is their LCM, and let there be some other number M, which is a common multiple, which means that A divides M and B divides M. Then our claim is that the LCM of A and B will also divide M. So again, same. Actually, it's exactly the same thing that we did earlier. Right? So if possible, let this not be the case. Then by division algorithm, M can be written as QL plus R. And can you proceed from here? What will happen now? Again, you'll end up seeing that R, I'll skip the steps in middle. Finally, what we'll see is that R is also a common multiple of A and B. And the fact that R is less than L is a contradiction. Okay. So I hope you can fill the details for this book. So in overall, if you look at this fourth point, all the four properties, you can look at them together. Okay, so point for ABCD, you can see how all of them are related to each other for LCM. And in fact, there is a much broader connection between BCD and LCM, which we are going to talk about now. So it turns out in mathematics in general, we often come across a term called duality. Have you heard this term duality in some other context? I don't know. For example, something as simple as, do you know Sevas theorem and Menelau's theorem? At least for those who may have heard these terms. If you're not, then you will be doing this in geometry at some point. But basically, Sevas theorem is about three concurrent lines. Okay, so three lines going through one point. And Menelau's theorem is about 3 points which lie on a line. So you see just the word point and line has been swapped around, and the same theorem becomes a new theorem. In the very same way, if I write these two statements side by side, right, you see how close the two statements are, even from definition. So GCD is the largest common divisor, and LCM is the smallest. That's my handwriting so bad. Sorry. Multiple. So right from the definition, now if I'll write the same thing on both sides. So let A, B be integers, and on the left side let G be the GCD, and the right side let L be the LCM. And if some D is a common divisor, then we have seen earlier that D is a divisor of G. And here we are saying if some M is a common multiple, then L divides M. So almost word for word there is a lot of symmetry between the two sides. And in fact, the connection is something like this. For the same two numbers A and B, consider the set S of all let's say positive divisors of A into B. Okay. So consider the set of all the positive divisors of A into B. Let's take some numerical examples just to illustrate this. Let's say A is 12, and let's say B is equal to 16. Okay, so A into B is a pretty big number, but if you write down all the positive divisors of A into B, of course you can group them as like for example 1 into 12 into 16, 2 into 8 into 16, like that. How much is that? So 190, right? So 1 into 192, 2 into 96, like that. You can list all the divisors in pairs of 2, correct? So the connection is, suppose I give you a number, in any such pair there will be two numbers, maybe n and n dash, such that n into n dash is equal to A into B, correct? So this is a interesting property that whenever you have such two numbers n and n dash, so this is what we are going to prove now. So claim is that, so let there be two numbers n and n dash such that their product is equal to AB. Then n is a common divisor of A and B if and only if its complement. In some way you can think of it as a complementation operation, right? N dash is a common multiple. So just as you may reflect some object in the mirror, in the same way this AB set is looking like a mirror in which you can reflect the element n to get n dash, and a common divisor becomes a common multiple, and this is a two-way relation. So can you see how to prove this?
Sir, I am aware of the proof for least common multiple and greatest common divisor being n and n dash. So I have to think about a general case.
Yes. So in subset, you see this is a generalization of that. There we are only saying that GCD and LCM, their product is AB, but here we are saying there is an entire set for which one element from this side and one element from the other side. They're like pairwise, the product is all AB.
Yes, sir.
So in fact, I mean that GCD into LCM property is going to be a corollary of this claim for us. Okay. Actually, this number 12 and 16 are too large. Maybe I should have taken some smaller number, which is easy to list out. Maybe 2 into 3 and 3 into 5. So 6 and 15, let's say. Then come down to 34. So my A and B are 6 and 15, and I'm just listing out the pairs. And from here on, it will reverse. So if you look at this list, you'll see the connection. On the left hand side, which are all the common divisors of 6 and 15. So 1, 2, 3, and 6, right? So 1, 2, 3, 6, these are the common divisors. And you see exactly the numbers in front of them, they are all the common multiples. Oh, yes. Not 16.
So 6 won't be a common number.
Yeah, not 6. No, not even 2 actually. So I think only 1 and 3 are the only two candidates.
Yeah.
Yeah, maybe again not a very good example, but maybe you can construct a different example and cross check. Okay, so we can try to prove this both ways. Let's say we start with because this is if and only if, which means that you have to prove two parts, right? First, let's assume that let's say we know that n be a common divisor. And then n dash, which is ab upon n. We want to show that this is a common multiple. So if n is a common divisor, which means that a is n times a1 and b is n times b1 for some two integers. And now I can define n dash in terms of this a and b. So n dash will be n a1 into n b1 upon n. This is n times a1 times b1. And you see how I can group this in two different ways to see that this is a multiple of a as well as b. Because if I can write this as n times a1 times b1 or n times b1 times a1, then you will see that this part is nothing but a and this part is b. So therefore, n dash is dividing a as well as b. So therefore, if n is a common divisor, then n dash is a common multiple. And I think this proof is pretty much reversible, that you can start from the last step and retrace the steps back to the starting point. Okay, so I'll give that as a exercise for you to complete. Yes.
So A should divide n dash, right? And B should divide n dashes.
Sorry. Yeah. I think the last step I wrote. Okay. So if you understood this, then do you see how this can be used to prove the fact that GCD into LCM is equal to A into B? Right? Because basically what is GCD? It is the largest such value of n, and LCM is the smallest such value of n dash. So they have to be paired with each other. Otherwise, what will happen if for example, so my claim is that if n is the GCD, then n dash is the LCM. So already we have shown that n dash is a common multiple. Now, if I find some other m which is smaller than n dash, which is also a common multiple, then what can I do?
Sir, then AM is also, sorry, NM is also AB.
No, I didn't follow.
Sorry, no. So I was saying that NM will also be equal to AB, right?
Yes, correct.
But
No,
then,
but why mn? I mean, m may be paired with some different number, not n, right? So yeah, that is the contradiction we want to use. So I define m dash, which is ab upon m, right? And because m is a common multiple, so this is a common divisor. And when you take the reciprocal, if m is smaller than n dash, then m dash will be greater than n. And this is a contradiction to the fact that n is the GCD. Right? So that is how the mirror image works. That basically you have two lists over here, list of all common divisors and all common multiples. So the largest common divisor has to be matched with the smallest common multiple. Okay, any doubts in this proof?
Yes, sir, I wanted to ask something, not about this proof, but we have for proving that LCM into GCD is A into P. So we have one more proof wherein we take A as P1 to the power alpha 1 and P2 to the power alpha 2, like that, and B as some other, like a product of primes and their powers.
Right.
So can that be used to prove this as well? Something like
So
that.
yeah, that's what I stated at the start. Maybe it can be done, but we have not done the prime factorization theorem yet, so we don't know that yet. If I mean, I am afraid that maybe in proving that we have to use this result. Then we'll go into the circular argument, right? What do you prove first? What do you prove next?
Yeah.
So if you are sure that you can prove all the prime factorization theorems without referencing this property, then that approach is perfectly fine. But we have to be careful when we write that argument.
Okay.
Okay. So then with this, I think at least the basic properties of GCD and LCM are done. One question for you to just explore and find out. We all know this property about two numbers, A and B. What about three numbers? What do you think will happen? Is it the case that LCM of the GCD of three numbers into the LCM of three numbers will be equal to their product? What is your guess?
Yes, sir.
No, sir. No, sir.
You're sure? Okay, let's take some numbers. Maybe A is 6, B is 10, and C is 15.
So the GCD is 1.
The GCD is 1, okay. And the LCM?
30.
30.
Then is it true? Is the product equal to ABC?
No.
No. But so this is not true, but something very close is true. But I will not reveal what that is. I'll let you explore and try to find out how can you modify this statement to make it accurate. Okay, so that is the homework for you. And in fact, there is nothing special about 2 or 3 numbers. There is a pattern in this kind of identities which can be extended to n numbers also. So see if you can discover that pattern. Okay. Okay. So then coming to the next part, we want to now look at what are called linear combinations of any two numbers. So if you have any numbers A and B, okay, this we already said before that all expressions of the form ax plus by, where x and y are integers, are called linear combinations. Of A and B. Okay, so in general, and x and y can be negative also. So it's not that these are necessarily positive. So one very important property is that this set S of all such linear combinations. Okay, there is a very specific property about this set. Can you make a guess what may be happening about this set? What elements will be in this set and will not be in this set? Like, for example, if A is 3 and B is 6, can 5 belong to this set ever?
No, sir, it would always be multiples of the GCD.
Multiples of the GCD, correct. So the claim is that this set S is precisely equal to the set of K times D for all where D is their GCD. Okay, so the set of all multiples of the GCD is exactly the set of the linear combinations of those two numbers. This is the claim. And this is one way of writing what we call, so that this is the Bezos theorem that was being talked about last time. Okay, so the spelling is B-E-Z-O-U-T, Bezos theorem. Actually, let me just check in the book if the Bezos theorem is exactly this or it is slightly different. What here is called Bezos identity. Yeah. So Bezos identity actually only talks about the GCD, that the GCD is a part of this set. That GCD can be represented as AX plus BY. But what we are saying is a bit more general. Yeah, the more integers of the form of this A something plus B something are exactly the multiples of D. So yeah, effectively it's the same thing. Okay, so how do we try to prove something like this? We want to prove, so there are two claims I'm making. Again, this is an if-and-only claim because basically there are two parts to it. First, what your claim is, claim one is that if some number belongs to this set S, then n is a multiple of D. And the claim two is that if you give me any multiple of D, then it will always be a part of this set. That will ensure that these two sets are exactly identical, right? The set of multiples of D and the set of linear combinations. So we have to prove both parts.
So can we start working like we take x and y, the GCD of x and y is 1, and then prove that it will be true, and then take x and y, GCD is greater than 1 maybe.
GCD of x, y. But see, the thing is,
Well,
first, which part you're trying to do? Part one or part two?
no, sir, in the general proof, I mean,
Okay.
I was thinking.
No, I think you need to define your approach bit more, because when you say x and y, the S set is an infinite set, right? So which pair of x and y are you referring to? So maybe you have to decide what is the starting point first. Yes, Adya?
I think we can use the property that if A divides B and A divides C, then A divides BX plus CY.
Yes, correct. So that is something which will definitely help us. The fact that if A divides two numbers, it will divide any linear combination of those two numbers, which we already understand. So that will definitely be useful. So can you see that we can use that to do part one? Right? Because D is the GCD of A and B, so D is already dividing A and B. Therefore, D has to divide any linear combination of A and B. So therefore, I think part one is quite simple. So claim one, if let n be a multiple belong to S, which means that n is equal to ax plus by for some x and y. And now in this equation, D divides A, D divides B, therefore D divides n. That's all, right? So part one is easy to do. What about part two? If D divides n, then it has to be a part of this set. That could be the maybe a bit hard.
The converse of the.
It's the converse, right? But it is not that trivial actually. Okay, so this is how we can start to approach this. First thing, let me do one thing. I mean, here the set S is the set of all linear combinations, but I am interested in, let's say, only the positive values for now. So let me just add that restriction that in both the set, I am only looking at the positive multiples. Okay. So S is the set of all the positive linear combinations. Note that x and y can still be negative, but as long as ax plus by is positive, I'll include that in the set S. Okay. So this is how I'm defining this for claim 2 or part 2. This is how I need to define the set. So let the set S be ax plus by positive, then x and y are some integers. So what can you observe about this set? See, whenever you have a set which has only positive integers or non-negative integers, immediately there is something that we already know, we did at the start, which should hit your mind. Yes, Raghav?
So the well ordering principle, there is
Well,
a
not
least.
close, right? So if I think it's not hard to see that this set S will be non-empty because I can choose some x and y, even if a and b are negative, right? I can choose a corresponding sign for x and y and make sure there is at least one element in S. So S is non-empty. So S will have a smallest element. So therefore, let's say I'll call that T. So that there will exist an element T in S, which is smaller than all the other elements of S, right? So this element T, firstly because it belongs to S, it will be ax naught plus by naught for some x naught and y naught. And S T will be the smallest such element. So what do you think will happen? What this T will turn out to be?
So the GCD,
It has to be the GCD, right? Because if it is, and we already know that every element T is already multiple of GCD we know, and we want to claim that all multiples of GCD are in this set S. So then the GCD itself will also be the smallest such number. Basically, D into 1 is D, that is the smallest number. So what
Sir?
now we, yes, go ahead.
Sir, x naught comma y naught belong to Z, right?
Z. Okay. So now we like to prove that T is nothing but the GCD of A and B. This is we want to prove. And out of that, so whenever you want to prove two numbers are equal, you can do it in two parts. So the first part is from the claim one, we already know that by claim one, D is already going to divide T because the fact that T is a linear combination of A and B, which are both multiples of small d. So therefore, D already divides T, or in other words, D is smaller than equal to T. So if I show the reverse, that if I show that T also divides D or T less than equal to D, either of these things, then these two parts together will force that T and D are equal, correct?
Yes, sir.
Okay, so this is what I want to prove, that I should T divide D. I want to bring your attention to one point here, which might help you to discover the solution on your own. D is the GCD of A and B, and we want to prove that some number T is a divisor of that D. Then what will it make T also? What we did right at the start of today's lecture. If I take a divisor of the GCD, do I get another common divisor?
yes, sir.
Yes.
And
Yes, sir.
conversely, if I show that T is a common divisor of A and B, then from what we did earlier today, you see that then T will be forced to be a divisor of the GCD also. So if we show that T is a common divisor of A and B, then are we done?
Yes,
Yes,
sir.
So in general, even like before we proceed with the proof, do you see how our thought process is working? We want to prove something, we convert it to something else, and we keep on showing that to prove this, we need to prove that. To prove that, we need to prove something else, right? This chain of converting, like rewriting the problem every time to something different. This is always for many Olympiad problems. This is how the thought process works. That whatever is the final conclusion, you have to backtrack from that sometimes. You can do progress from both directions, from what is given and from what is to be proven. So you have to make both the meets end at different times. So here we are doing the backtracking. So to prove this, it's enough to prove that T is, let's say, T is a common divisor of A, and by symmetry, the same thing will happen for B. So if T divided A is proven, then we are done. And at all points, we have to keep in the back of our mind what are the assumptions we are making, which will help us to do it. See, T is not just any element of S. Any element of S will obviously not be a divisor of A, but T is the smallest such element. So the smallest has to be used in some way. see, these things are recurring again and again. The same thing which we did for LCM a few minutes ago, we are going to think something similar here also now.
What if we prove a contradiction that T does not divide A,
Okay.
which means T will not divide B or Y also?
No. Why is that the case?
No, sir,
Okay.
because AX plus BY is equal to T, right?
Yes.
and
Okay.
then
Yeah, yes, I agree. Correct. Then what will happen?
so then A does not, okay, T does not divide A. So whatever remainder we get when we do AX like mod T, that will be something that will be the remainder that we get when we do it with B, like that T minus that remainder.
Yeah, I think you are on the right track. Basically, what we want to do is we want to come up with another element which is even smaller than T, which can be represented in this AX plus BY form, because then that will be a contradiction, right?
Yeah, so we need to prove that T is not the smallest. Like using this, we need to show that T will not be small.
Yeah, so I mean that remainder is what we can use. So if T does not divide A, then I can write A as QT plus R, correct? Where R is between 0 and T. So if we can somehow show that this R is also linear combination of A and B, then we are done. And that should be easy to do, right? If I just rearrange this equation, I take everything to one side. This is simply R is equal to A minus QT. And here I can substitute the formula for T, AX not plus BY, and just rearrange a few things. And you see, I can regroup everything as A times something and B times something, correct?
Yes, the T will replace by AX.
So the coefficient of A will be 1 minus Q X naught and B will be minus Q Y naught. So what I have shown here that R is also a linear combination and also greater than 0. So therefore R will also belong to the set S, which contradicts the choice of T as the smallest element.
Yes.
So, but how are we sure that 1 minus QX naught and minus Q naught means, like, why are they positive?
No, so the thing is, X and Y don't have to be positive. That's what I said. X and Y could be positive, negative, as long as the total sum is greater than 0. I am okay to put it in the sum. See, otherwise, if you ask X and Y to be also positive, then the value of X plus BY will only increase, right? How will you get the GCD that way? You have to have some combination of plus and minus to get the GCD, correct?
Yes, sir, yes.
Okay, so therefore, just to backtrack that, what have we proved now? So we proved that T divides A, and similarly T divides B. So if these two things are given, therefore by the theorem which we did some time ago, that so T is a common divisor of A and B, and therefore it has to be a divisor of the GCD also. Therefore T divides D also. And so basically D divides T and T divides T, then this forces that T and D are exactly identical. So in other words, the smallest element of this capital S which is T, is also the GCD of A and B. Okay. So therefore, what we have proven now finally is that the S, which is the set of all positive AX plus BY, is also the set of all multiples of D. And now if you want, you can remove this greater than 0 sign also, because the same set can be reversed on the negative side, right? If I flip the sign of X and Y, the value of this will also reverse. Okay, so this will not. Okay, this is a very powerful theorem actually. And in fact, now knowing this theorem enables us to do a lot of things. In fact, you can go back and prove the GCD property once more using Bezos theorem. Okay, that is something maybe you want to try. That so if you know this theorem now, you see it's very easy to do the original theorem now. So the property that we are trying to do last time. So let A, B be integers, and let D be the GCD, and let G be another common divisor. Then we are trying to prove that G divides D. How can you prove this using Bezos theorem now? Yes, Raghav.
Yes, sir. So we know by Bezos theorem that D can be written as ax plus by for some x and y integers.
Yes.
And since G divides A and G divides B, ax plus by can be written as G times a1x plus b1y,
Yeah, we
where
are done. Right?
sorry. Yes,
That's all. Right? If G divides A and G divides B, G divides any linear combination of A and B. And we just saw that that set of linear combinations includes the GCD and all multiples of the GCD. So that's all. So yeah, once you know Bezos theorem, you see how powerful it is. The proof that we took much more effort to do with Bezos theorem, it's much easier to do. Of course, the caveat is Bezos theorem itself is not that simple to do. So either way. So and this is a very important toolkit to add in your number theory. Okay, and there are a few other things also which we can very easily do using Bezos theorem. The one which is called Euclid's lemma. And actually, I think some of the proof that you were trying last time, we are using Euclid's lemma without having proven it. So Euclid's lemma is that if there are integers such that A divides the product of B and C, but A and B are co-prime, then A divides C. Okay. So in other words, if a number is dividing the product of two numbers, but out of that it is co-prime to one part, then you can be sure that the divisor is going into the second part. Okay. Again, not hard to see how to do this using Bezos theorem, because what is given is the GCD is 1. So that is something we can try to use. So if the GCD of A and B is 1, we can find numbers there exist x and y such that ax plus by is equal to 1. And then what can we do next? We have to bring C into the picture somehow, right? So what can we do?
Sir, here there is no positive factor, like it can be negative also.
Yeah, x and y can be negative also. Yes, Raghav.
so we multiply the equation by C.
Okay, so if you multiply by C, you get ACX plus BCY equal to C. Then
We know that A divides we
yeah,
know that
basically
A divides AC X, and we know that
correct.
A divides BC.
Correct. A divides the first part obviously because there is A there, and A divides BC also. Therefore, A will divide that sum. Okay. So this is Euclid's lemma. So suddenly after Bezos theorem, lot of things start to become very simple to prove. Okay. Any doubts in what we've done so far?
Sir, I had a doubt.
Yes, tell me.
Sir, in the second claim which we had made, that if D divides N and N.
Sorry, Adya, I think your voice is a bit low. Can you speak up?
Sir, in the second claim of Bezos theorem, if
Okay.
D divides N and N, then N belongs to S. I
Yes.
did not get the last step, that how we get N belongs to S.
Okay. Okay. So, oh, yes, you are right. Yes, I think we did not do that. That is correct. What we only showed that the smallest element of S is the GCD. So that part you understood?
Yes, sir.
Okay. So then what you can do, right? Once you know that D can be written as the sum AX plus BY, and N is a multiple of D, then whatever is that factor, so whatever that N upon D is K, let's say, if you multiply the whole thing by K, what you get AKX plus BKY? So once D can be written as a linear combination, any multiple of D can also be written as a linear combination, right? If I just multiply the coefficients.
Yes, sir.
Okay. So yeah, I think I missed to state that. So therefore, not only D but all multiples of D are also going to be in S. And in the claim one, we already showed the reverse, that if there is some element in S, it is going to be multiple of D. So the bijection is complete from both directions. Okay. Yeah, important point to complete the proof. Okay, so then I think we are moving to almost what is the last part of this divisibility topic. So next week, of course, we'll have the exam, and after that, we'll come to prime numbers. Then what Anushka was saying earlier, that prime factorization, all of those things will give us a new insight into this topic altogether. And in a way, you may ask that why am I keeping this distinction separated? Why am I not bringing prime numbers here? The reason is somewhat related to the fact that I talked about this last time also, that the division algorithm, GCD, LCM, these concepts are not applicable for only integers. They're applicable for other kinds of objects in mathematics, such as polynomials also. And in some of those other domains, there is no such thing as a prime number. But even then, all of these things are true. Division algorithm is true, GCD, LCM is true. So almost word for word in the whole presentation, wherever you see integer, you can replace it with polynomials, and almost the same thing will happen. Of course, there will be some changes, but so that one-to-one correspondence is very easy to show here if you don't talk about prime numbers. But once we get into prime numbers, then we are talking about only integers. Then those things are not generalizable to other domains. Okay? So, I mean, of course, these things are not important for us for Olympiads, but I mean, one of the purposes of these lectures is also to give you an idea of what is the other mathematics out there. It is not just Olympiad. So now the last part is linear Diaphontine equation. Okay. So the Diaphontine is a sort of, you can say, adjective form of a mathematician called Diaphont. I suppose name. Also don't know.
Sir, what is the second word you've written?
Yeah, let me Diaphontine. Diophantin. It's actually a proper noun. There's a mathematician who I think was Diaphantus. I'm not able to remember why that word came. See, Diaphantus of Alexandria. So he was almost 2000 years ago. Diaphantus was a mathematician who laid the foundations of a lot of the number theory that we use. That is how that word came. Okay? Diaphantin. And all it means is equation which has integers. So that, I mean, a very complicated way of saying an equation where all the variables are integers. That's all it means. And linear part, of course, means that there are no square or cube terms. So that is what it means. So in the most general sense, if you have n variables, let's say x1, x2, x3, xn, then a linear Diaphontine equation would look like a1 x1 plus a2 x2 plus a3 x3. Okay, the whole thing is equal to some b. Or some y. Okay. So here x1, x2, x3. So here a1, a2, a3, and b, they are all given to be some constants, and x1, x2, x3, and everything is integer. So all ai, xi, b, they are all integers, and the job is to find all the solutions which satisfies this equation. So that is the most general sense. But we'll start with the simple version. So I mean, the most simple, of course, there is only one term, let's say. So if let's say the simplest case is that if given ax equal to b, where a, b are integers, solve for z, solve for x. So this is something I think we all already know maybe. But just for completion, why don't everybody try to write this properly with all the corner cases taken care of? Because here AB can be 0, something can be non-zero. Yes, Gaurav, are you giving the answer to this problem?
Yes, sir. I hope I'm audible.
Okay, no. So, okay, you will not on chat.
So,
No, so wait till you give the answer. Let's give everybody some time to think.
okay, sir.
I didn't get the second last line that you've written.
So you are given an equation ax equal to b, then a and b can be any integers, and you have to solve for x, which is also an integer. So what is the solution set of x which will satisfy this equation? Okay, so Gaurav, can you tell?
Yes, sir. So if A is equal to 0 and B is not equal to 0,
Okay. Okay.
then no real value of x satisfies the equation.
Correct. So the solution set is empty.
Yes,
But
sir.
if a is 0 and b is non-zero, then correct, this cannot happen. Okay.
Sir, if A is not equal to 0,
Okay.
B can be any value, then
Okay.
x is equal to B by A.
This will be correct.
Yeah.
Or otherwise, I will write this.
And sir, yes, sir, there's another case.
Okay.
So that if A equal to 0 and also B equal to 0, then x
Okay.
belongs to real numbers.
Integers. Okay. We are going to talk about integers.
Okay, yes, integers, sir.
Okay, so these are three cases. In most typical cases, if a is non-zero, then the solution set will have exactly one element, b by a. But the two corner cases could be either if all the coefficients are zero, then any value of x is valid. And if a is 0 and b is non-zero, then no solution is valid. So this is the full characterization of this ax equal to b equation. And I think maybe this is something already we cover in the MPI lectures. So you might be familiar with this. Okay, just to revise. So then from the starting point, what is the next step? Instead of one variable, what if we have two variables? So now consider
Sir, I
the
think
equation.
there would be one more case where b is equal to 0 and a is not equal to 0.
But won't that get covered in case 2 already? Because in that case, the solution set is already having the element 0,
Oh, yes, yes.
right? So when a is not equal to 0, b being 0 or non-zero, both cases can be combined. Okay. So now let us go to variables. So let a be c. Let there be three constants given to us, and now we are trying to solve ax plus by equal to c. So now solve this for x and y both being integers. This is what we want to do now. And now we have a good amount of sort of background experience about how this ax plus by expression works, right? The Bezos Theorem gives us a lot of powerful ideas. So maybe even first trying to let's do this in 2 steps. Let's first take care of the corner cases. Okay. So like for example, the corner case, because you have three elements A, B, and C, there being 0 or non-zero will be total 8 possible combinations, which is 0, which is non-zero. We may not want to write all of those, but at least how can you club them efficiently?
So we can start with one of x and y is 0.
Yeah. So I mean, basically, first thing you'll observe is that, let's say, I mean, I divide my whole space into two parts. So case, so instead of case, kind of part 1, where let's say b is equal to 0. within that there will be 4 subcases, right? A0, B non-zero, etc. But what I observe is that if B is equal to 0, then the equation becomes Ax equal to C, which is already we have solved before. So in this case, X will have to satisfy the previous problem. So X is as per one variable solution. Okay. So if I call this first part which I did as the one variable case, okay, one variable case or one variable solution, then I don't want to keep rewriting the same thing again and again. X will simply satisfy that condition and y can be any value, right? Because y is not coming in the picture anymore. So like that, like one big chunk of cases were just eliminated in one line. In the same way, if A is equal to 0, then the reverse will happen. So by equal to C. So instead of x and y, it will be y and x. So now y will be as per the one variable case and x can be any integer. So like in big chunks, I'm eliminating a number of cases. So that makes things much easier for me. So now I can consider the case when both A and B are non-zero. Okay. And now in this there will be two subcases. What if AB are non-zero and C is 0? And what if AB is non-zero and C is also non-zero? So this we need to look at. In fact, I think we don't need to separate this also. We can combine these two together.
Sir, if A and B are non-zero and C is equal to 0, which would mean AX is equal to BY.
Yes,
Sir, Ax should be equal to minus b.
minus B.
Yeah, minus BY.
Yes. But then still that doesn't give us the full list of what are the x and y which satisfy that relation, right?
Sir, we will get the ratio, right?
We'll get the ratio, that is true. So basically all x and y which are in that ratio will be the answer. But and we'll try. So what I want to do is let's not take C equal to 0 as a separate case. That's not required. Just in the single variable case, the RHS being 0 or non-zero doesn't matter. Once the coefficients on LHS are all non-zero, we don't need any further subcases. So here also, once A and B are non-zero, doesn't matter whether C is 0 or not. Okay, so try to do this general case now. So AX plus BY equal to C, where A and B are guaranteed to be non-zero. So now what will happen? So in your view,
Sir,
will this
C
always have a
divides-
solution? Yeah, tell me. Anushka, you were saying something?
Yes, I was saying C divides AX and C divides BY. That
C
would be-
divides AX and C divides BY. Were you think that
So
is
we had,
necessary?
we had no. I mean, like we had done some theorem, the Bezos theorem on this, so we could use that and
Yes. So because of Bezos theorem, what restriction will be there on C? Can C be any number?
So it has to
Raghav?
be, yes, sir.
no, sir, it has
The GCD should divide C.
Yes, correct. So if so I think it's a good time to define the GCD of A and B. So let D be the GCD of A and B. Then the cases can be, so case 1, if D does not divide C, then the solution set is empty, correct? Because
yes,
then
sir,
what
so
will
it is
happen?
not solvable.
It is not solvable. LHS is divisible by D, RHS is not divisible by D. So there is no way to proceed here. So what it forces is that D has to be a divisor of C. Okay. So maybe let's say C is equal to D times some K. Now, how do we proceed? We still want to find all the values of X and Y which satisfy. Yes, Raghav.
Yes, sir. So now our equation is AX plus BY is equal to C. So we can, and we know that D divides A, B, and C. So we can divide the equation by D.
Yes.
And so we'll get, so let A equal to dA1, B equal to dB1, and C equal to dC1. Then we get an equation A1x plus B1y is equal to C1.
Correct.
We
So
also
you
know
see, yeah, we have removed one factor of D from the whole equation. So we have simplified the equation. And now what can you say about A1 and B1?
so the GCD is 1.
Right?
So
They are left with co-prime numbers. Okay. So that's a good start. But before we proceed, Raghav, we have to be careful that because we want to find the entire solution set of the original equation, this process has to be reversible, right? So if
yes,
I
sir.
start with the x and y, which is a valid solution of the original equation, that will give me a valid solution of the new equation and vice versa. So we just need to check that once, but I think that everybody can verify. Okay, as long as you understand this point. Okay, you can proceed.
Yes, sir. So now by Bezos theorem, A1, there exists integers x0 and y0 such that A1 x0 plus B1 y0 is equal to 1.
Correct.
And now if you multiply the equation by C1, we get A1 times Cx0 plus B1 times Cy0 is equal to C1.
Okay, I multiply everything by C1. Okay, so A1 x naught C1 plus B naught B1 y naught C1 is equal to C1. Okay.
Yes, sir. So x0 C1 and y0 C1 are solutions to this equation.
Yes. Right. So if you see here, this part can be x and this part can be y. So we have found one pair which satisfies this. So this is the new equation. If I call this equation 1, the original one, and this is equation 2. So we have found a valid solution for equation 2, right? So x naught C1 comma y naught C1. This pair satisfies equation 2. Equation 2 means this one. And from this, how can you obtain the original equation? I mean, ax plus by equal to c. We have to multiply everything by d, right? The GCD which we had removed, if we add it back. So if I starting with this, if I just multiply everything by d.
So we'll get A1D, that is A, and then B1D which is B, and then C1D which is C.
Correct.
Sir, why will D be a part of the solution?
Oh,
Because if
sorry.
you multiply the
It will get absorbed in the So in fact, this satisfies 2 and also 1, right?
So you mean X and Y both are 1?
No, not x and y. So what you are maybe I'm getting confused here. See, a1 times this plus b1 times y is equal to c1. So x is equal to x naught c1, y is equal to y naught c1. This is satisfying equation 2. And now when you multiply the whole thing by d, from this multiplying by d, we get a1d which is a. So a times x naught c1 plus b times y naught c1 is equal to c1 times d, which is c. So again, x naught c1 and y naught c1 are the x and y which satisfy the original equation. Okay. So if we find one solution of this, so basically what this gives us one idea is that let's not take numbers which have a non-zero, non-one GCD, right? We can start with a and b which have GCD of 1 because then that is a simpler problem to handle. And anytime you multiply that with some number like d, you will get a case where the GCD is not 1. Okay? So this equation 2 is easier to deal with. So we can always look at that first. So here we found one pair x naught y naught, but do you think there will be only one pair? After you find one pair x naught y naught, can you think of some clever idea by which you can have more solutions of the same equation? So what we know is that a1 x naught plus b1 y naught is equal to c1. This x naught y naught pair satisfies. But see what you can do. I want to keep the total equal to c1, but I can change x naught and y naught at the same time. so that one is increasing, the other is decreasing, something like that. What can we do?
Sir, you can maybe change like add
Mhm.
multiple of GCD to one and subtract the multiple of GCD to another.
Yes. Now in this case, A1, B1 are co-prime, we already know. So then it is a bit simpler to talk about that. So then what can we do? So this is the trick. What if I add and subtract a copy of AB or A1, B1 without changing the LHS, right? And what can I do now?
Maybe take out A1 and B1 common.
Correct. So now I can rearrange this as A1 times X0 plus B1 plus B1 times Y0 minus A1. So basically, I have added increased X0 by B1 and decreased Y0 by A1, so that the total contribution is still 0.
Yes.
And I can keep on doing this, right? I can keep adding a copy of B1 here and taking a copy of A1 here as many times as I want. So now can you see what could be the most general solution?
Yes, sir.
Right.
Yes,
So it will
sir.
be X0 plus some T times B1
And
Y0.
Y0 minus C times A1.
Right. So of course, to do all of this, we need the first solution. So this X0, Y0 we still don't know, but we know they will exist. So see what Bezos theorem says is that such X0, Y0 exist, whose linear combination is equal to the GCD. How to find those numbers we have not done yet, but we'll come to that soon. Okay. So if X0, Y0 is a valid solution, then this any expression of this form is also a valid solution. But again, this is we have to find a solution set. How do we know that there isn't some other term which does not land in this series? This is an infinite series, right? Because t can be an integer. But maybe there is some x1, y1 which is not part of this series and which is also a valid solution. So can that happen? So if let's say there is some completely different pair of x1, y1 which also satisfies the equation. So equation 2 meaning, let me write it again. So equation 2 is a1x plus b1y equal to c1. Okay, so in other words, a1x1 plus b1y1 equal to c1. This is given. So now the question is, will this x1 y1 pair be forced to belong to this family of series we already have, or this will be a new term altogether? So think of it this way. See, when we went from x0, y0 to the next parent, we added b1 here and subtracted a1 here. Like, can you take a smaller step than b1? Instead of adding b1, is it possible to take a smaller step and land somewhere in between x0 and x0 plus b1? Like a half step, maybe? Will that be okay to take a half step like that? Or will that cause any issue?
So
And
actually,
maybe,
it may not be, it may not work. I mean, if you're dealing with integers, it may not work.
exactly. You see, the problem is the fact we are eating. If see fractions are allowed, then any step you can take, right? But
Yeah, correct.
see, whatever
Taking
increase
value
you
of
do for x0, same has to be compensated by decrease by y0. And both of them have to end up being integers. So that will not happen if the step you are taking is not a multiple of b1 or a1. So
Yeah.
this is what idea which we have in the mind, but now we have to convert it into a proof that my claim is that x1, y1 is also of the same type. So x1, y1 pair is also like x0 plus tb1 and y0 minus ta1 for some t. This is what I want to prove. That there will be some t which will exist, which will have x1, y1 also as part of the equation. Yes, Rahul, you see how to prove this?
Yes, sir.
Okay, just wait a couple of minutes. Okay, but is the sort of mental visualization clear for everybody what's happening? And we can take some example. Let's say concrete equation 5x plus 3y is equal to 11. Let's say. And so what is one solution of this equation?
1 and y is 2.
1 and 2.
Alright.
Okay. And so with the process that we did right now, can you find what will be the next solution after this? So I increase x by 3 and I decrease y by 5. So I'll get 4 comma minus 3. Is that also valid solution? Yes. And you can see, right, if I try to do anything in between, like if I increase by 3 by 2, the y will no longer be integer. So there is no way to do anything in between. So this is like a arithmetic progression. So the next term will be, the difference will always remain constant, right? Always x will increase by plus 3 and y will decrease by minus 5. So this is force. This periodic behavior is force. There is nothing in between that is possible. So this is what we want to prove now. Okay, Raghav, so how do we start?
Yes, sir. So we start with like a contradiction.
Okay,
Suppose if this is suppose yes,
so if this is not the case, okay,
yes, sir. So x1 can be written as x naught plus k x naught plus k1
hmm,
and y1 can be written as y naught plus k2, y naught minus k2.
okay.
Yes.
But
Now we
I mean,
substitute this in the
maybe
equation.
I didn't understand fully. See, when we say that, claim that this is not the case, then there has to be some restriction on K1 and K2, right? Otherwise, in general, some K1 and
Yes,
K2 like this
K1
will
and
always
K2
exist.
will not.
So K1 less than B1 and K2 less than B2. Sorry,
Okay.
So no, they'll not be multiple,
A2.
right?
Sorry,
And instead of saying, yeah, instead of saying less than K1 or K, this thing, I think we just say that K1, K2 are not multiples of T. That's what where T does not divide K1 and K2. Correct? Okay, so
Yeah.
then what will happen?
Then after you substitute this in the equation, you get a1 x naught plus a1k plus by naught minus b1k
It will
is
be
equal
K1 and
to
K2, right? Different indices. Okay, then
so then you know that a1 x naught plus b1 y naught is equal to c.
yes. So out of the LHS, A1 x naught plus B1 y naught, because we already know x naught comma y naught is a solution. So that will cancel with
Yes.
the C on the RHS, right? So
Yes,
what
sir.
will be left with?
So you get a1 k1 is equal to b1 k2.
Okay.
We know that a1 a1 and b1 are co-prime. So by
Yes.
Euclid's lemma, a1 should divide k2.
Correct. So A1 divides the RHS,
Yes.
but A1 is co-prime with B1. So by Euclid's lemma, A1 is going to be a divisor of K2.
Yes, sir.
Okay.
And
Then
similarly, b1 is going to be a divisor of k1, which is contradiction.
why is that a contradiction?
Because we assumed first that k1 does not like a1 does not divide k1.
No, we assume T does not divide K1, right? We never said anything about A1. Or I don't know if your starting point was different.
Once.
Oh no, I think you're right. My mistake. So yeah, actually, what we want to say is that what is the difference between x0 and x1 that should not be a multiple of b1. So where k1 is not a, so b1 does not divide k1 and a1 does not divide k. That was the right sort of assumption in the proof by contradiction. Correct. So we have exactly proven that what we had assumed to be false. B1 does not divide K1, that's what we are getting in the end. So our assumption is wrong. So therefore, B1 divides K1 and A1 divides K2. But I mean, almost there. I guess that part we can do that. I mean, it may be that x1 is x0 plus some t1 times b1 and t2. So why is the t also same? But that is just a minor. They have to be the same because otherwise the value will not come out to be c1. That is fine. Anushka, you want to add anything?
Sir, actually, I had some different idea, and I haven't made the whole proof yet. But what I thought, when we have one solution, that is a, so say a x1 and b y1 is equal to plus b y1 is equal to c. So we have the solution x1 y1. Then let us say that like the remainder that we get when we divide a x1 by b is say a. And so the remainder that we get when we divide C1 by BY1, that will be like BY1 minus K. So we have to make something so that this ratio, I mean, this remains constant. So we'll have to always add the same variable. That is, we'll have to always add Y1 to AX1 so that we get the same, it is divisible. Like that.
Okay. Now, I think your idea is right, but I may have a problem with the last couple of sentences because whenever you say that we have to add the same ratio to restore that answer, there that is where maybe we need to formalize that in the notation somewhere. So if you can try to write it properly and send it, I'll take a look. Okay. I had a slightly different approach. I think it will turn out to be somewhat similar to what Raghav said, but I think we can proceed even without contradiction. So let me just say that let x1 and y1 be another solution. Okay, satisfy the equation. Okay, and x0 and y0 we already know is satisfying. What if I just subtract the two, right? So I know a1 x1 plus b1 y1 equal to c1 and a1 x0 plus b1 y0 equal to c1. If I just subtract the two, I'll get x1 minus x0 times a1 is equal to b1 times y1 minus y1, right? Opposite y0 minus y1. And here I directly apply Euclid's lemma. So by Euclid's lemma, I mean a1 divides the RHS and a1 is co-prime to b1. Therefore, a1 divides y0 minus y1. And similarly, b1 divides x0 minus x1. And here itself, you can rearrange the things to see that basically the a1 upon b1, I mean, whatever this ratio y0 minus y1 upon a1 will be equal to x1 minus x0 upon b1, which is equal to t. And therefore, if you just rearrange this, therefore, this forces that x1 is equal to x0 plus tb1 and y1 is equal to y0 minus tb. So we'll get the same thing at the end, but without having to call it proof by contradiction. Okay. So then, what is the conclusion of all of this? That I mean, we are talking about the case where you are to be non-zero. Okay, returning to the original problem where the GCD of the A and B is not necessarily 1. That was something we did for simplification. So original problem when AB is non-zero, AX plus BY equal to C, the equation we want to solve. So what is the solution set of this looking like? So we said that let D be the GCD of A and B, and there will exist x0, y0 such that D is equal to ax0 plus by0. And we also said that if C is not a multiple of D, then the solution set is empty. So we are dealing with the case where D divides C. So let's C equal to D times K. So now here what we have is x0, y0 satisfy this equation. Ax0 plus by0 is equal to D. I can multiply the whole thing by K to get ax0 K plus by0 K is equal to D into K is equal to C. So x0 K comma y0 K is a solution. So x0 K comma y0 K is a solution. And then what are the other solutions which you can generate by adjusting x naught and y naught in both directions? So here, I mean, before we go to C, this equation ax naught plus by naught equal to d, this is itself will have the family of solutions of the form x naught plus something, y naught minus something, right? So what are those something going to be? We did the case when the GCD was 1. That was very easy. Now the GCD is not 1, it is d. So what will the adjustment? You see the adjustment itself be multiple of d. So it will be t times b and t times a, right? Okay. Maybe if you're not following this part, just to go back quickly. I mean, if I wrote the same equation when the GCD was 1, it was looking like ax naught plus by naught equal to 1 and x naught plus b1 and y naught minus a1. This was the family of equations t times 1. This was what we got. Now when I multiply this whole thing by d, so when I multiply this by d, right, what is going to happen? b1 d will become b, right?
Yes, sir.
Okay. So this is the family of equations for ax naught plus b1 naught equal to d. But from d I want to go to c, so I have to multiply everything by k again. So the most general answer is going to be x naught whole thing by k. So basically k times x naught plus tb, k times y naught minus t. So this is where t can be any integral. So this is the entire solution set of the original equation. Provided, of course, that d divides c. Okay, so just maybe I'll give a couple of minutes to write down whatever you want. So this is like the full treatment of two unknowns, x and y, in linear Diaphontine equation. And you can imagine that the complexity, in the linear sense, the complexity is not that high. Here, instead of 2 terms, if you have 3 terms, 4 terms, you'll have more freedom. Can you think of that? Suppose you have x, y, z, all three are there. Ax plus by plus cz equal to d. That gives you more freedom because what you can do is, let's say, keep the x constant and only adjust y and z, right? You increase y and decrease z like that. So you'll have a lot of freedom like that. So, but in principle, it is doable. It is all linear. So things are very simple. When you go to quadratic equation, like suppose you have an equation like ax square plus by square equal to c. That is where things start to become much more complicated. And right now we don't have enough theory to deal with that. In fact, even in Burton's book, you'll find that this whole thing is covered almost to the end of the book. So what is called the Pell's equation, PEL, Pell's equation, is about quadratic Diaphontine equations, and they require a lot more heavy machinery in number theory to deal with that properly. So, and it is, I won't say it's not outside Olympiad coverage, but number of problems where you read such an advanced theory is very low, and particularly at RMO Informal level, definitely. So if you are going to the final rounds, then you need more like theoretical tools. But right now, this linear system, if you understand properly, that is good enough to solve lots of problems. Okay. So maybe just to conclude this topic in terms of what we have covered in theory, right? I think we have covered pretty much everything from first 2 chapters of Burton. Okay. First chapter was induction, and second chapter was this basic divisibility, GCD, LCM, etc. There might be few properties here and there which I didn't mention, but they should be easy to prove as corollaries of Euclid's lemma or Bezos theorem. So you can check those out and finish that on your own. So I mean that just to give an idea of what will be the syllabus, so to say, for next Sunday's exam. So first 2 chapters of Burton. If you do the practice problems, I think you will be in good shape. And while you are doing the problems, if you get stuck anywhere, you can just ask the doubt on our group, which somebody will respond.
Sir,
Yes.
So in the bottom number theory, the second principle of finite induction, I didn't understand what it was.
So that was the strong induction that we're talking about. So where the induction hypothesis is itself very strong. In normal induction, what we say is that if some property is true for k, then we have to prove it for k plus 1. But some statements are much harder to prove, where it's not enough to assume that the property is true for k. We need to know that the property is true for all the numbers from 1, 2, 3, 4 up to k. So if I know that the property is true for all the first k integers, then the induction step is to prove that it is true for the next integer. So if in some problems you require to use strong induction, where normal induction is not sufficient.
Yes.
So for example, we saw an example of this when we did the powers of 2 problem, right? Every number can be written as the sum of distinct powers of 2. So there what we did was, if your number n is there, which is written as 2 raised to k plus m. So we sort of take away the largest power of 2 that comes right before your number. So you are left with a number which is much smaller than n. Now in normal induction, if you are only given that n minus 1 satisfies the property, then we don't know that m can be written like that. But when in strong induction, m is part of that whole series, right? 1, 2, 3 up to n minus 2. So wherever this m lands, we already know that m can be written as the sum of powers of 2. And so we can use that in the proving the induction step. Okay. Okay, so I mean, the last thing I want to talk about this linear Diaphontine equation is that you get these kind of puzzles. You have seen them, right? You have a 3-liter can and 5-liter can. Have you seen those kind of puzzles where you want to somehow extract, let's say, 4 liters of water? So
Yes.
let's say there is a large reservoir which has infinite amount of water. Okay, and you have 2 cans which are 5-liter and 3-liter, and there are no markings. And somehow you want to extract, let's say, 1 liter of water using just these 2 cans and this infinite water. Can you do it?
So,
Can you raise your hand if you already know this kind of puzzles?
Sir, I don't know, but I have some idea.
Okay, so maybe if everybody has not heard, let's take a few minutes to think about this puzzle. And how is this related to the Diaphontine equation? Yeah, I think at least several people have heard of these puzzles. Okay, so those who have not heard, give it some thought. What can you do? What you can do, of course, is you can use these 2 cans to take water from that reservoir, pour it back. But the problem is you cannot take half water. Like you cannot judge with your eye that okay, this is like 2.5 liters. That is not allowed. Or some people have very creative ideas. You put the 2 glasses side by side and look with the eye where it is half and half. Those kind of clever tricks are also not allowed.
Record the answer.
Okay. And do you see how this could be connected to Diaphontine equations? Because I mean, very easy connection I'll say is that suppose instead of 5-liter can, I give you 6-liter can and 3-liter can. Now can you extract 1 liter water no matter what you do? No, right? Because anything you do will be multiples of 3. So there is no way to reach 1 liter can. It's the same way. So, but because GCD of 5 and 3 is 1, therefore this should be possible. But how to do it? And the question is not only this problem you will solve, but suppose I ask you a much harder problem tomorrow. Where maybe I'm now giving you a 1000 liter can and so maybe 551 liter can. I hope these are co-prime. And now you are supposed to extract 337 liters of water. So the numbers are suddenly very big.
I wanted to ask something. So the volume of this can, the maximum volume will be 551 and 1000, right?
Yes.
Or like, so if we just add a little bit, it will overflow. So it is just
It is just that much, yes. And you can assume that we are going to be careful. We don't drop even single drop of water.
Yes, sir.
Oh, by the way, I completely forgot to do one topic. Euclid's algorithm. That is an important piece of this theory. I will do it next time, okay, after the next exam. Okay. I maybe already know Euclid's algorithm to find the GCD of two numbers. So we like to cover that. I completely forgot to do that. Okay, so somebody can tell the solution of the 5 liter, 3 liter, and 1 liter problem. What do we do first? Wait, can somebody raise your hand if you know? Adya?
Sir, we fill the 3 liter can
Okay,
and then pour it into the 5 liter can.
okay,
Then we again fill it and again pour it into the 5 liter can.
okay. So then what will happen?
So in the 3 liter can, we get 1 liter.
Yes, correct. Because in the first case, what we did, the 5 liter can was only filled up to the first 3 liters. So remaining 2 liters was empty space. So next time when we fill 3 liter can, start pouring. After the 5 liter can gets full, at this point, the left hand side has exactly 1 liter remaining. Okay. Probably, I mean, if you count in the number of steps required, this is probably the fastest. Is there anything which takes even less number of steps? I don't know. So now count how many times did you fill the 3 liter can?
2 times.
2 times. And I mean, at the end, you will pour out the 5 liter can. So you'll be removing 5 liter can once. So you see, effectively, we are constructing the solution of the equation 3 into what plus 5 into what is equal to 1. And the answer is plus 2 comma minus 1. Because we are filling the plus 3 liter can 2 times and we are emptying the 5 liter can once. So in the same way, we have a harder problem. Let's say I have a 7 liter can and an 11 liter can, and I want to somehow extract 3 liters. Then what do we need to do?
So same steps, fill 7 liter first.
Oh, sorry, then unfortunately my choice of numbers is not.
Next.
Then let's
So
say
it
2
will be
liter.
2 into minus 2 comma minus 1.
Yes, in that case that was again simple. Let's say 2 liter can, 2 liter you want to extract. Then what will happen?
Sir, it's pretty similar.
Okay, but I hopefully this will require more steps, or is it also coming very
Sir, plus 5 minus 3.
plus 5, so 7 into plus 5 and 11 into minus 3. So which means I have to fill the 7 liter can 5 times, right? So
Sir, or 7 into minus 2 and 11 into 1. Sorry, not minus 2. No, minus 2.
no. What will be the next solution be? In the if I subtract from here 5 comma minus 3, what will be the solution below this one? I have to subtract 11 minus 6 and plus 4, right?
Yes.
So both are possible, 5 comma minus 3 and minus 6 plus 4. I mean, whichever will take less number of steps. Maybe more. I think the first one will take less number of steps, right?
Yeah, that will be 8 steps and this one will be 10 steps.
10 steps. Okay. But you can see how to do that, right? So if let's say we execute this algorithm. So first I'll fill the 7 liter can. The other one is empty. Then you pour it. So now the 11 liter can has 7 liters of water. Again, we'll fill the 7 liter can. And so the thing is, if I give you a separate bucket, which is just empty, this is much easier to do, right? I'll fill the 7 liter can 5 times, pour it into this, so I'll get 35 liters. And then just take away the 11 liter can 3 times. So 35 and 33 will become 2 easily. But because that third, like empty bucket is not there, I have to juggle it between these 2 cans only. That is why I have to alternate between pouring and subtracting, just to manage the space. But the operation we are doing is exactly that. 7 into 5 and minus 11 into 3. Okay, so first time we poured into 7 and transferred. Second time again we'll pour and transfer. So when we do that, now this time the RHS will have, it will not get full, it will get full completely, but here I'll have 3 liters remaining. So now I'll throw away the right ones. So again the right is empty. Now transfer the 3 into that can. Again repeat the process. So again I have to fill it once and transfer. So now I have 10 liters in that one. Then again I fill it one more time and transfer. The whole thing will not get transferred. I'll have 6 remaining over here. I have to discard this one and transfer the 6. And then again I'll have to fill 7 over here and transfer. So 6 plus 5 11, and I'll have 2 remaining. And this 5 minus 4. Okay. So in all, how many times I filled? I filled exactly 1, 2, 3, 4, 5 times I had to fill, and 3 times I had to empty. That is why 35 minus 33 is 2. So that's what we are doing, just in a more complicated way, as I said, because there is no second derivative of R available. But yeah, when we do Euclid's algorithm and how to find this initial solution, that's the whole question. This x naught, y naught. Bezos theorem tells us this solution will exist, but how do you find it? Do you keep doing trial and error, or is there a better way? So that is the answer which Euclid's algorithm will give us next time. Okay, so we'll stop for the day, but just to quickly finish on one point on the last time's puzzle. So if you remember what we were doing last time, we were talking about we have to send 4 symbols A, B, C, D, and where we know A occurs 50% of the time, let's say B occurs 25% of the time, and C and D occur 12.5% of the time. Okay, and just to make things concrete, let's say I have to send a text file which has 1000 letters. And in that 1000 letters, this is the distribution, which means there are 500 times A is coming, 250 times B is coming, and C and D are both coming 125 times. Okay, this is the size of my text file. In the normal mapping, if we give 2 bits per symbol, okay, let's say 0, 0, 0, 1, 0 and 1. If we give this one, then how many bits will the file size be? It will be 1000 letters into 2 bits per letter, right? So the size of my file will be 2000 bits. Or if you want to write it in bytes, you divide by 8, you get 125 bytes. Oh, sorry, 250 bytes. So you have to send a 250 bytes file to send your 1000 letters of information. But now we are saying, instead of giving 2 bits per symbol, we are trying to be more clever. We know A is occurring more frequently. So A should be given a smaller symbol, and others should be given larger symbol. So can anybody suggest what can that look like? And see, the important thing is unique decodability. We don't want ambiguity. So
A will be 0.
Okay.
B will be 1 0.
Okay.
And C will be 1 1.
And D?
D is thinking about. So 0 1.
So any scheme you propose, you have to make sure that it is uniquely decodable. If somebody can send a string which is ambiguous, then you are in trouble, right? So are you sure that this scheme does not have any issue like that, where somebody may have confusion what is the message being sent? What do others think?
There is ambiguity.
There is ambiguity. Can somebody give an example of a sequence which cannot be decoded uniquely?
So 0 1 1 0.
0 1 1 0, because this can be
0 1 as D and 1 0 as B, or it can be A C A.
yes, correct. So you see there is a problem. Adya, you have a different scheme.
Sir, A is 0 0.
Okay.
B is 1 1.
Okay.
C is 0 1 0.
Okay.
D is 1 0 1.
Okay, but then you're increasing the bits, right?
Yes.
You want to save bits.
It works, but the bits they don't matter.
Right. So this is uniquely decodable maybe, but then we are not reducing, we want to compress the file. So I think at least the first starting part was on the right track, that A, let's say give A0, that part is correct. And we give B as 1 0. So the important property which I want to introduce here is what is called prefix free code. So prefix free code is a code in which no representation is a prefix of another representation. Do you understand what is meaning of the word prefix? Prefix is something that comes before, right? So I mean, For example, the word batata has bata as a prefix. So bata is the prefix of batata. So in the same way, the problem with your scheme, Anushka, was I forgot what was it. So D was 0, 1, right? You see, the symbol of A is a prefix of this. That is where the confusion comes. So this is what we want to avoid. We want a prefix-free code. So this is the code which I'll propose, and I'll allow you to check that it is prefix-free. So let's say A is 0, B is 1, 0, C is 1, 1, 0, and D is 1, 1, 1. Now you can check that there is no case. See, if it starts from the middle, there is no problem. So see, this B is occurring here, that is fine. But it is not starting from the first bit. So when you are decoding from left to right, there is no confusion. Do you see that? And I can also show this as a tree. So the tree, if you've not heard of graph theory, you will think of a physical tree with leaves and everything. I'm not talking about that tree. This is a tree of possibilities. So I start from the root node, which is empty. If I go to the left side, I'm adding a 0. If I go to the right side, I'm adding a 1. So here I'm writing 0 and 1. Then from 0, I can write 0, 0, 0, 1. From 1, I can write 1, 0, 1, 1. So you see how in every step of the tree, the number of possibilities will keep doubling, right?
Here's what I found.
Oh, there's something I missed. I should have taken more space to write this. But in this tree, do you see where my A, B, C, D are? So A is here, correct? Where is B? B is here, 1, 0. C is 1, 1, 0. And D is 1, 1, 1. So you see how all of them are lying on different branches. So if I get a, let's say a receiver gets a symbol like 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 0, 0. And I want to find out what is this. So what I do, I start from the left hand side and I walk the tree. So whenever I see 1, I have to go to the right. Whenever I see a 0, I have to go to the left. So I start from here. So I see a 1, so I go to the right. Then I see a 0, I go to the left. As soon as I reach one of my codes, I know I have decoded one symbol. I cut it and I start again. So I keep doing that. So that is how I can cleanly cut my sequence into this series where there is no ambiguity. Is everybody following how this process is working? So like that, one symbol at a time, you can keep decoding and there will be no confusion. So this is what we call a prefix-free code. So we are out of time, but I'll suggest now, if I use this scheme to encode my original text file, which has 1000 letters, can you compute now how many bits will I require to transmit this file? And hopefully, I think you can cross-check that you have achieved both targets, that the file can be uniquely decoded and it takes less number of bits to send. Okay, and then maybe once later we'll see, is this the best we can do or we can do even better? So that will be the question after that. Okay, but I'll leave all of us with this. Thank you. Bye. So I'll once I confirm the details of the test, I'll post on the WhatsApp group. Okay. Okay. Thank you. Bye.
Bye, sir. Thank you, sir.
Bye, sir.
Bye, sir. Thank you, sir.